Hello guys, welcome back to Meson African Motives. Still working on our revisions for power machines and 5. In this case, we shall be working on the thermodynamics of gases as a revision from the question paper of November 2020. So we shall just quickly rush through the questions. I think we introduced this and talked about the formulas that are important for each and every process that you are going to have. So this is a gas of mass of 1,32 kilograms at 20 degrees Celsius is compressed. All right, so this is being compressed from this pressure, from this temperature. So we can just take our information that we are given. So we've got the mass of the gas, which is 1.32 kilograms from a temperature, which is T1 in this case, the initial temperature, 20 degrees Celsius. So if we add 273 to convert to kelvins here, gonna add 273, that is going to be 293. So that's 293 Kelvin in this case, all right? And also from the pressure to this pressure, from this pressure in kilopascal, so that is our initial pressure, which is P1, which is taken at 105 kilopascal, all right? So that is at 105 kilopascal in this case, to a pressure, which is the final value, which is 1,500. So that's P2 in this case, right? Which is 1,500 kilopascal, okay? Again, we are given it is taken according to the law, PV to the exponent of gamma. So this one is our gamma in this one. So once we use this PV to the exponent of gamma, it means we are working with an adiabatic process, all right? So you are supposed to know the type of process that you are dealing with. So this is an adiabatic process that uses PV to the exponent of gamma in this case, which is the same thing as what you do if you are working with the polytropic of PV to the exponent of n is equal to c. You're going to see that you're going to have the same formulas or the same application. I shall explain that as we are seeing the formulas. Then you're also given the specific heat capacity at a constant pressure. All right, so this is at a constant pressure, which is Cp. So you're given at constant pressure, Cp, that's 1,005 kilojoule per kg Kelvin. If it is at constant, it can be given at constant volume, which will be given as Cv. At constant pressure, that will be Cp. And also we're given the characteristics gas constant, which is 0,285, which is the value of R in this case, all right? So we've got the value of R, which is 0,285. That is kilojoule also per kg Kelvin. All right. So that is what you are given, and this is an adiabatic process. Remember, we are given this from the law, PV to the exponent of gamma is equal to C. So the first question is 2.1, calculate or to find the value of gamma in this case, and that is 4 marks. All right, where can we obtain the value of gamma? We have got Cp, we have got the characteristics of gas constant, which we have. All right, so if you have to check, there's a relationship between Cp and Cv, and also R and Cp and Cv. If you check on your formula sheet here, I just wanted to get you here. These two formulas that we have here, we've got R, which is equal to Cp minus Cv, and also we have got the gamma, which is Cp over Cv. All right, so I'm going to take these formulas, try to make them work for us in this case. All right, so that's question 2.1. We are supposed to calculate the value of gamma in this case. All right, so as we saw that the value of gamma is given as Cp over Cv. And also R is equal to the difference of Cp minus Cv in this case. So we can calculate our gamma if we have the value of Cv. All right, we do not have value of Cv. This is Cv, not Cp. All right, Cv, not the way that I'm writing here, C and V, like this. So if we can be able to calculate the value of Cv, which is with respect to the volume, that means we can be able to calculate the value of gamma. But what limits us is that we do not have the value of CV. We do not have this. So where are we going to obtain this? We have a relationship that we mentioned here. So we can make CV the subject, all right? If we take this to the other side, it means it is going to be positive, or you can just substitute the value of R there, which is 0.285 is equal to CP, which is 1,005 minus CV. So to find CV, going to transpose to the left-hand side, it becomes a positive. Then we transpose this to the other side, it becomes a positive, and this value becomes a negative, but CV becomes a positive, all right? So that will be 1,005 minus 0,285, like that, right? So there we are going to have the value of CV. And that was going to give us 0.72, all right, 0.72, which will be in kilojoules per kilogram Kelvin, all right? So with this value that we have just determined, it is going to enable us now to find the value of gamma, because we said our gamma is going to be given as CP over CV, and we have the value of CP, which is 1,005. Over CV, we have the value of CV that we calculated here, which is 0.72. That is going to give us the value of gamma, which is going to be 1,3958, something like that. Okay, so you can just take an approximation to 1 decimal place, all right? So that's our gamma is going to approximate to 1,4 in this case, all right? That's an approximation that you are going to use on your calculations, all right? So you can use the 3 decimal place, which is fine, but you can just have an approximation to 1 decimal place. So the question is, we're done actually to find the gamma. Then we move on to the initial volume, all right? The initial volume. Remember, we have the mass, we have got, all right, there's a lot that we actually have here that we can actually take into consideration. I'm going to need the value of gamma here, which is, we said is 1,4. So if we are to check here, we've got a lot of things that we can consider in our calculation to find the value of what? The value of the volume, in this case, at initial conditions, which is V1. We've got T1, we've got P, we've got M. So remember from our formula, PV is equal to mRT. I said that if you are using at initial condition, this will be P1, V1, and this will be T1. And that is the best formula because we've got everything there. So you can just find our V1. If we divide this by P1, we also divide this by P1. So this will cancel. So you're going to have our V1 as mRT1 over P1. So we can just substitute because we've got everything in this formula that we actually need. We're just going to substitute everything that we are given here. We've got the mass of the gas, which is 1.32. So that's 1.32 times the gas constant, which is 0.285 times the temperature at initial condition in Kelvin. That is 293 over P1, and P1 is 105. So that means here we can have this direct, right? If you've got another formula that we can let us work with, let us know so that we can work with that formula. It can be very, very helpful. So that was going to give us something like 0.04977, like that. So it's going to be 105, all right, cubic meters. Remember, this is volume that we are calculating. So you're going to have this in cubic meters, okay? Then we move on to the other part. Then they need us to calculate the final volume, which is V2. All right, so there we need to calculate V2. So we do not know the value of V2. So for V2, there are so many formulas again that we can actually put into consideration. All right, so let us just write it aside. This is 2.3. So remember, we are supposed to calculate V2. So like I said, there are so many formulas that you can put into consideration. From this part, we can have, or we can work with this formula between the temperature, pressure, and volume. which can give us whatever that we want. All right. Also, we can go back to the easiest formula because there we want the volume. So we can use this formula here, but where we see the n, we are going to use the gamma. So it will be P1 V1 to the exponent of gamma is equal to P2 V2 to the exponent of gamma. All right, so I'm going to explain this one. It's been a lot of videos that I've explained about this type of a formula. From this one, I think, guys, we have explained a lot, and now you have a basic understanding of that formula. So let us try to change and work with something, and you see that it's actually one and the same thing that you actually obtain. Or like I said, if you know this, you can just have it as the final formula, but you can go back because we've got P1, we also have V1, we calculated V1. So P1, V1 to the exponent of gamma is equal to P2, V2 to the exponent of gamma, and we want to calculate the value of V2. So we can just divide here by P2, That means we are going to be left with the V2 gamma in this case is equal to, this is same as P1 over P2 times V1 to the exponent of gamma. So to remove this gamma here, we're going to multiply by the inverse, which is 1 over gamma. The same thing, 1 over gamma on this side. So as we can see that here, this will cancel and we remain with V2, which is the exponent here affects everything. It affects V1. It also affects P1 over P2. So on V1, it's V1 to the exponent of gamma like this. Then we multiply by 1 over gamma, which is this one. So as you can see, this will cancel. We are left with the V1 to the exponent of 1, which is V1. But for the pressure, we do not have the exponent there. So it is going to remain as P1 over P2, everything being raised to the exponent of 1 over gamma like that. All right, so that is, we can manipulate our formula. Even if you choose the one that I indicated before, you are going to have the same thing. And I think I explained about this formula when we're dealing with the air compressors. So the manipulation of the formula is the same. How you manipulate the formula is the same. So V2 is going to be V1. We've got the value of V1 here, which is 1,05 into P1 over P2. Remember this, we have sometimes they give you a ratio, but here we have got the values P1, 105, P2, 1,500. So it's going to be 105 here over 1,500 to the exponent of 1 over gamma, which is the gamma that we calculated. We approximated to 1 decimal place as 1,4. So it's going to be 1 over 1,4 like this. So that is going to give us V2 in cubic meters, which is going to be 0,1571300 like that, which is 0,157 in cubic meters, right? So that is how we could have calculated our V2 from the V1 that we had here. So I've got 3 marks for that. Then we move on to the final temperature. Again, we've got V2, we've got V1. So there are a lot of formulas that we can actually use. We can calculate the final temperature from T1, since we've got T1 and P1 and P2. So there are so many formulas that you can use. You can go back to that formula that I indicated before. All right, so let me just write here because we might need this V1, 1,05 cubic meters, V2, which is 0,157. All right, so that's 0,157 cubic meters. All right, so maybe we might need these values later on. So like I said, we can, the formulas that you're going to have to find T2, which is the delivered temperature in this case, there are so many formulas that we can put into consideration. So let's see which one is the best and how can we find this value in this case, all right, of T2, which is the final temperature. So in order for us to find the final temperature, which is T2, we can go back to PV because we've got this value of V2, we've got R, we've got the mass. So you can go back to PV. PV is equal to MRT, which is our traditional method in this case. So for T2, it means this must be P2, V2, T2. So to find T2, it's simply going to divide by MR. We divide by MR here. So this will cancel. That means we've got the delivery temperature in this case, I mean the final temperature, which is T2. So T2 is going to be given as a P2 V2 over MR. All right, so that's it. We're gonna have our T2 there, which is P2. That's P2, it's 1,500. P1, all right, we're working with P2 there, sorry, that's P2, 1,500. All right, times V2, which is the volume that we just calculated now. Remember V2 there, we got 0.157 cubic meters. That was the value of V2 here. And also, we've got the mass of the gas, which is the mass here of this gas is given as 1.32 kilograms. So you're going to substitute 1.32 kilograms. All right, times the gas constant. If we are to check, we've got our gas constant, which is 0.285. So this is 0.285. All right, so this is going to give us the value of T2. There are so many ways that we could have calculated this T2. So all you just need, here's our calculator. If we are to simplify, just put a fraction there, 1,500 times 0.157 over 1.32 times 0.285, like this. So that is going to give us 6. All right, this one is already fixed to 3 decimal places. Just shift setup. We go to the fixed on 6 there. So 3 decimal place, that is the one that we see here. So it's going to be 625.997, right? 625.997 Kelvin, right? So it is because of the decimal places, we are using rounded off figures. So even if you are to use another formula, you are going to see that it is going to affect you at the end. All right, remember there is this formula that we saw from our formula sheet. Let me just explain also from there. From this formula, that is the one that we referred here. It's just one and the same formula, but here we are working with what? We are working with the gamma. So we are going to use this formula and see how we're supposed to have this T2. So there we have got so many things. So we saw that T2 over T1 can be given as P2 over P1 to the exponent of gamma minus 1. All right, so that is gamma there minus 1 over gamma, which is equal to, for the volume, it is going to be V1 over V2 to the exponent of gamma minus 1. We have P2 and P1, we've got V1 and V2. So there you can just play around with any formula that you want. If you want to write in terms of T2 is equal to this, it means we are going to have T2, which is equal to T1 into P2 over P1 to the exponent of gamma minus 1 over gamma. Or if you want to write your T2 in terms of this V1 and V2, it means you're going to multiply by T1 this side. So T2 is going to be equal to T1 into V1 over V2 to the exponent of gamma minus 1. So there we've got a lot of things to consider. So let us just substitute our values and see what we're going to have here. T2 is equal to, remember, T1 is 293. So I've got 293 into P2, which is 1,500. So I've got 1,500 over P1, which is 105 to the exponent of gamma minus 1. That's 1,4 minus 1 over 1,4, which is we are going to have the value of T2. So that's just because we are using different figures. Here we've got exact values. It's not from any rounded figure. This one, we rounded off the values of V2. So the values are not going to be the same, but this one is the exact answer because we are using original values from the information that we're given. There's nothing that we calculated here. So this one is going to give us the exact answer that we're supposed to have, which is going to be 626.38249 and so on, which is 382 in Kelvin. So like I said, from this formula, we have the exact answer because we used original values. It was not by any figure that we calculated. We are using exactly that we had from our given information. If you are to use this one again, you're supposed to have a similar question, a similar answer there. T1 This one is the original value that we have T1, which is 293. All right, into V1 over V2. So V1, it is us who calculated. So here we are not going to have exact answer. It is just going to be at least close to that one. But because remember, it is us who calculated V1, so it's a rounded off figure, which is 1,05 over V2, which is also a rounded off figure. So these answers, they are not going to be exactly the same. All right, so the gamma there, which is 1,4, so it's to the exponent of 1,4 minus 1. So that was going to give us the value of T2. And this was going to be 626,59 Kelvin in this case. All right, so that's we have got the value of T2 in this case. All right, so that is the idea there of our question. Then the work done, in this case, 4 marks for that. All right, we have the work done. So remember that work done, we can actually have it. All right, let me just show you from the formula sheet so that we can move on together. These are the formulas that we can actually play around to find the work done in this case. All right, so we've got, all right, let me check here. There's another part before this. Before the work done, we need the change in internal energy in kilojoules, 3 marks for that. All right, so the change in internal energy first. All right, so there is going to depend with which value that you are going to use in this case for T2. So you pick any of the values that you're going to use here. So it's for me, I'm just going to use this one, the exact one, because there we obtained it from the values that we had. We did not calculate these values. These were original values that we had from our given information. So I'm going to use my T2, but you can use any T2 from the one that you got, all right? So use the T2 that you got in a case that you are going to need this temperature. Use the one that you got or the one that you have. So the first equation was the internal energy, the change of internal energy, which is 2.5. So the change in internal energy is going to be given by which formula? All right, if you check here, this is what we have. We are not actually given the formula direct for the change in internal energy. It's just given as the mass times CV times the change in T. So we can have this, or sometimes you might calculate from Q and work done if you have this, but here we can just use this one. Since we have got CV, remember we calculated this, we calculated that where the CV from R and CP, if you still remember that part, all right? So we are going to use this, calculate our change in internal energy, which is given as the mass times the CV into T2 minus T1 like this, all right? So as we saw that our CV, we calculated that from the CP, we got something like, it was 0.72, yeah, it was 0.72 kilojoule per kg Kelvin, all right? So we're just going to substitute. We've got the internal energy there, which is the mass of the gas, 1.32 times the specific heat capacity according to constant volume, which is 0.72 into the change in temperature, that is T2 minus T1. All right, so T2, remember, we use the one that you calculated. Me, I'm going to use this one, 626,382 minus T1, which is 293. So here you are going to use your own value, the one that you calculated from your best formula, right? We choose which one, the one that you obtained, use your value as it is, all right? So if I'm to use this value, I'm going to obtain my change internal energy as 316,846, and this is in kilojoules, all right? Then the last question was to calculate the work done, which is 4 marks. From all this information, where can we obtain the work done? So there are also so many formulas that we can use for the work done. If you have to take into consideration here, we've got these formulas, the work done from this formula, the work done, so many formulas. So I'm just going to take this one, number 10, work done, which is P1 V1 minus P2 V2 over gamma minus 1. All right, so since we have got the gamma in that case, all right, so I'm just going to use the last one. All right, so let us just have it here. So that's 2.6. We said we are going to have our work done as P1 V1 minus P2 V2 over, it was given as gamma minus 1. All right, so that is the formula that I'm going to take because I have P1, V1, P2, and V2. I have everything in this case. So that's our work done is going to be P1 105 times, all right, we're going to multiply V1. Remember, we calculated V1. We got 1,05 minus P2. We have P2 here, which is 1,500 times V2. We calculated V2 here. We got 0,157 cubic meters over the gamma minus 1. And we have the value of gamma in this case, all right? So remember, we are given the gamma there, which is 1,4 minus 1. So this is going to give us the work done if we apply this formula direct. So there we are going to obtain a negative, all right? So that's negative 313,125 kilojoules, all right? So the purpose of the negative there, if we are to consider it, it means we are having, actually, it means the work done it means the work is being done in the air. All right, the work is being done in the air. That's having a negative value. So in conclusion, what I can just say is that if you are working with the thermodynamics of gases, as you can see, you can use different formulas obtaining the same thing. So what you just need is for you to know the formula to work with. Which formula is best for you? Use the best formula. That is what I can put into conclusion. So let us just revise, guys, as we are preparing for the exams that are ahead of time, working with your formulas and understanding each and every process that you have in your syllabus.